Hello, this is DeepTalksDiga, and today I'm going to be talking about this derivative problem here. This problem includes pretty much every single rule. That's why I wanted to do this one. And what we're looking at here is we have chain rule right here. We have logarithms. We have logarithmic differentiation, trig functions, inverse trig functions, power rule. And if you look down here, we have product rule, which we'll also have to do up there, I think. And then we also have an inverse derivative. So we got a lot going on here. But to do this, I'm just going to take it step by step. So I have this problem written down somewhere else, so I'll remember it to go back. But to start with, I'm just going to find f prime of x. And to do that, I'm going to set this whole thing. Let me get a better marker. I'll do this one for now. I'm going to just say this whole thing is equal to alpha, okay? Now, the reason I'm doing that is because I can split this into different things. And the way I'm going to do that is I'm going to just name every single piece of this. I'm going to start over here. Always start on the inside here. I'm going to name this function ln of x a. I'm going to go outside here and name that sine of ln of x as b. And notice we have sine of a in here. Now right here, x squared is going to be c, x cubed is going to be d, and this difference is going to be e. We got the full inverse cosine there, which is going to be f. And then this whole sum is going to be alpha, right? But I'm not going to put that down to save space. Now what I'm going to do from here is, first of all, what I want to talk about is how I can define a variable as being three different things. I can define it as a constant, I can define it as just a variable, or I can define it as a function. And each of those are going to behave differently. So these variables are going to correspond to functions, which means I have to treat them like functions. Now, what we have here is I'm going to just start with alpha, right? What is alpha equal to? Alpha is equal to b plus f, right? And I'm just going to keep writing these down. But yeah, I'll just keep going. And let's start with b. What is b equal to? Well, b is equal to the sine of a. What's a equal to? A is equal to ln of x. F is equal to the inverse cosine. F is equal to the inverse, that's not cosine, the inverse cosine of e. E is equal to c plus d. C is equal to, minus c minus d. C is equal to x to the x. And d is equal to x to the third. All right, so now I have everything set up here. And what I'm going to do is I'm going to take the derivative of each of these on their own, and I'm going to just substitute things in. So what we're looking at here is, this is just a sum, so I'm just going to put d over dx up here, so we know these are the derivatives. And instead of doing this, I'm just going to draw an arrow. And when I draw this arrow, just know that means this is the derivative. So b plus f is going to become b prime plus f prime. Now sine of a is going to be a chain rule. So remember, that means we have to multiply the input, the derivative of the input, to the outside. And then what's the derivative of sine? That's cosine. Remember, we just flip it, and then we're still left with a inside. The derivative of the natural log of x is just 1 over x. Pretty simple. Now here, the derivative of the inverse cosine is going to be, I'll write it out, negative 1 over the square root of 1 minus x squared. Now this is also chain rule, remember, so I'm just going to make that negative 1 an e prime. Actually, x should become e here. And the best way to remember these is to just write them down again and again. So that's really the only way you can do that. Here, c minus d is equal to c prime plus d prime. C, the derivative of c, is going to be, I'm going to write it down here, and then I'm going to explain it, because this is like a super important one. I'll get to the explanation for that in a second. And then the derivative of x third, that's just a nice product rule, 3x squared. So now, where did this come from? Well, we can't really just take the derivative of x to the x, because if you think about it, is this an exponential? Is this a power? It's going to be an exponential. Because we can do what's called logarithmic differentiation, where we can say x to the x is equal to e to the ln of x to the x, because e to the natural log of something is equal to some constant function variable is equal to the input right there. Now, because of our log rules, we can just say this is equal to e to the x ln x. And then we're just left with this derivative, which is pretty simple. Derivative d over dx of e to the x ln of x. Now, if you remember, well, you may not remember, but the derivative, I'll write this down here. The derivative, no, that might not be visible. I'll write it back over here. The derivative of e to the f of x is just going to be equal to f prime of x, e to the f of x. And this is just a simple chain rule. This one's just easier to remember because it's with e to the x. So what I'm going to do is I'm going to say this is equal to, what's f prime of x? I'm going to get this. And let's look. We have an e to the f of x function. So what's the derivative of x ln x? Well, let's think about it. We have x and natural log of x. Let me check something. Yeah, that's fine. And now we look at their derivatives. The derivative of x is 1, derivative of natural log is 1 over x. And then we just multiply across. So we got ln of x plus x times 1 over x is going to be x over x, which we can simplify down to 1. However, just that's something to note. That means it can't be equal to 0, which makes x can't be equal to 0, which also makes sense because the natural log cannot be equal to 0. So that's just something to note. So here we're looking at ln of x plus 1, that's our f prime of x. And then we're left with e to the x ln x. Right? Erase this again. Now, if you remember, e to the x ln x is equal to x to the x. So we can just simplify this down to ln of x plus 1 x to the x. You can leave it as e to the x ln x. That's also perfectly valid. But I like simplifying, even if it makes everything more difficult. It just looks nice. Let's fix that. All right. So now all we got to do is just plug things in. Right. So let's start with b prime plus f prime, because we're looking for alpha prime. Right. And then what we do from there, let's plug in b prime and f prime. What is b? Where's b? B prime is going to be alpha prime cosine A, and f prime is equal to negative e prime over square root of 1 minus e squared. Okay. And I'm just going to keep going. What is a prime? We get 1 over x. And what I'm going to do is I'm going to put cosine of a in the numerator. A is ln of x, so we get cosine of ln of x over x, because remember we got to multiply by a prime. And also, yeah, that's correct. Plus negative e prime. E prime is, well, negative c prime plus d prime over the square root of 1 minus, in parentheses, c plus d squared. Okay. From there, I'm just going to remember this is here, and then I'll plug that back in later, because now we're dealing with this negative c prime plus d prime over square root of 1 minus c plus d squared. So we'll just plug in c and d, and also c prime and d prime. So our final answer should be f prime of x, because remember we're looking at alpha prime, f of x is equal to alpha. F prime of x should be equal to cosine of the natural log of x over x plus negative, and remember we got our ln of x plus 1, x to the x, plus 3x squared from there, all over, and then our beautiful denominator 1 minus x to the x plus, should that be plus? Yes, plus x to the third squared. Fill that in the top. All right, look at that. So now we have f prime of x, and what I'm going to do is I'm going to write this down so I don't forget it, and then we're going to move on to the next part, which is the derivative of g of x, g inverse of x. So we're going there now. All right, so for this part, we're looking at the derivative of g inverse of x, where g of x is equal to the tangent of e to the x. Now, to do this, we first need to remember the derivative of this function g inverse of x is going to be equal to 1 over g prime of g inverse of x. That's just the inverse derivative rule. I'm going to change markers back to this one, because this one works a little bit better. But that's how we're going to do this. This one will be a little shorter because it's very difficult to find more complicated inverse ones, because it's more difficult to take the inverse. But here, the way we take the inverse is we're going to start by saying this g of x is going to be y. Y is equal to tangent of e to the x. And to find the inverse, we're going to flip the input and output. So now we're going to end up with x is equal to tangent of e to the y. And we want to isolate y, because that's going to be g inverse. That's our output, our new output. To do this, we take the inverse tangent of both sides. Inverse tangent of x is going to now equal e to the y. And then we just take the natural log of that. Natural log of tangent inverse of x is equal to y. Because remember, natural log of e to the whatever is equal to whatever the input is. So now we got our inverse function. So I'll write that up here. I'll erase that a little better in a second. We now know g inverse of x is equal to the natural log of the tangent inverse of x. All right. Now, what we're going to do from here is we're going to differentiate this. And to do this, well, obviously we got to find the derivative of g prime, derivative of g, which is g prime. And that's pretty simple. We're just going to look at the chain rule. And so I'm just going to set up a simple chain rule. Usually I would set up the whole thing, but we'll do it this way. All right, nice chain rule. So now I'll put g prime here. G prime of x is equal to, so if we have secant squared of e to the x, times e to the x. E to the x, secant squared e to the x. And that's just because we start here, input the e to the x into the derivative of tangent of x, and multiply by e to the x, just like that little box method, because it makes everything simpler. Now we're just going to plug things in. And that means we're going to look at 1 over e to the g inverse of x. I'm going to fill that in later. And we have secant squared of e to the g inverse of x. Right? And that's just going to be equal to 1 over e. I'm going to put the 1 after just so I have room. Ln of tan inverse of x. Yep, I'm doing this right. I had to pause for a second because there's so much going on. Secant squared of, again, e to the natural log tangent inverse of x. Whew. This is why I waited for the 1. So this is now our derivative of the inverse of that. So now I'm going to put these together and differentiate. All right, so looking at this, I have this monster of an equation. Now, what I could do is, by the way, I just turned this into a reciprocal just because it was easier to look at. And to be honest, this is so long that I don't think I have time to go through this entire thing in a single video. So I might do that. I'll probably do that in another video. If you want to try it on your own, you can. I'm gonna work it out, but it's too long to explain actively. Now, what I would end up doing is I would look at this as a quotient rule, because if you notice, that's going to be a reciprocal or multiplying. So it's going to be this entire problem, well, this function divided by this function and the derivative of that. So it's gonna be like the derivative of this times this minus the derivative of this times this all over this squared. And that's just like, that's a monster of a problem. Again, doing problems like this where you do everything is probably the best way to practice these calculations and make them quick. So honestly, I would recommend trying the problem, but it's a very long problem. But yeah, I mean, if you want to do it, go for it. But that'll be in this video. This was Deep Thoughts with Deegan, and I'll see you next time.